Good morning, here we are. Once again, it's the physics video lecture, Physics 190, video lecture 8. And today we're talking about power series, Taylor series. Very amazing version of the Taylor series here in the complex plane. So I had a couple of ingredients up on the board last time. I think I made a mistake at one point that I'll correct. What we have now is, from Cauchy's integral formula, the derivatives. We have the nth derivative at z is equal to n factorial over 2 pi I closed contour f of zeta d zeta zeta minus z to the n plus first power. I believe we missed that at one point. Okay, so that's the formula we're going to use from last time. We also have this very important series expansion that the sum over z to the nth power, infinite series, 0 to infinity, integer powers, equal to 1 divided by 1 minus z, when the magnitude of z is less than 1. So you're inside the unit circle. Okay. So what we're going to do is find our Taylor series, our infinite series power series expansion for functions in the complex plane. And we'll set that up, since these were the preliminaries, with the integral formula. So for the Taylor series, we're going to use the integral formula, which is actually implicit right here for n equals 0, namely f of z is equal to 1 over 2 pi I integral f of zeta d zeta zeta minus z, okay, to the first power. And then we'll carefully look at our domain that we're going to be working in. So I'll put that right here. Let's draw two concentric circles here, and we're going to put the point about which we expand, we'll call z sub 0, in the center of both concentric circles. This here is our curve or contour, so zeta is always on this outer contour here. Okay. And I'm going to put z is always on this inner contour here. Actually, just this inner set of points. This is actually the contour that we're integrating. Okay. And this is a point z. Because what we can then say is that zeta minus z sub 0 is always greater than the magnitude of z minus z sub 0 by this construction here. And that's what we'll use. So z is, there's no contour here. Z is simply a point on that circle, but we're doing that to be sure we see this relation here. Okay, so let's go ahead and repeat this and make something out of it this time. So once again, we'll start with the f of z from the integral formula. F of zeta d zeta. Now, the zeta minus z, we're going to factor out this case, yeah, let's write it this way. Zeta minus z minus z sub 0. Z sub 0 minus z. There we go. So there's our denominator. That's still identically the same thing. The zeta minus z and the z sub 0's cancel here. But now we'll factor this out. 1 over 2 pi I. Zeta. We'll take zeta minus z sub 0 out of here. And then we'll have 1 minus z minus z sub 0 divided by zeta minus z sub 0. Okay, all under the denominator there. And here we see that this ratio has a magnitude less than 1 because the denominator has larger magnitude than the numerator. So I'm just going to accent this thing here. So this thing in the red bracket is itself just a complex number. Right? It's a combination, just a complex number of magnitude less than 1. So what we can now do is use this expansion right here. So we now have 1 over 2 pi I closed contour, so f at d zeta, f of zeta d zeta, f of zeta d zeta. Zeta minus z sub 0. And now we have this sum here. We have this infinite series. So we have the sum from n equals 0 to infinity of this z minus z sub 0, zeta minus z sub 0 to the nth power. That's all under the integral, but not everything has to be integrated. The z minus z sub 0 to the n will actually be outside the integral. This will be integrated. So when we do that, we can rewrite this as, in fact, I can write this all in one fell swoop. Let's have a look. So summation n equals 0 to infinity. We'll put in our integral 1 over 2 pi I integral f of zeta d zeta. Here we go, zeta minus z sub 0 to the n plus 1 and z minus z sub 0 to the nth power. And I'll even just say f of z now has this form. And we see what I have in the parentheses here is the derivative, the nth derivative divided by n factorial evaluated at z sub 0. So this is a Taylor series. These were shown to exist. Good. So yeah, just one more time, directly underneath here. So yeah, we have Taylor expansion n equals 0 to infinity. I'll just call it c sub n z minus z sub 0 to the nth power. And those are the coefficients But on the other hand, we now know that functions of this form exist, and they're going to have all the good properties, in particular, going to be infinitely differentiable in this form here. We're not going to have any problems. We have one derivative, we have all infinity of them. These are complex coefficients, these are just powers. Good, so I'll go ahead and put the C sub n over to my I. However, just as importantly is simply that it is the nth derivative at z sub 0 divided by n factorial. We use this formula a lot, but when we're writing out a power series, if we have it in this form, then we have it. Okay, we don't have to do this. And then this will be really useful for calculating certain other things and for calculating integrals that we've already done a little bit of. Good, so there's our Taylor series. And if you need some examples, just take your favorite functions. You've got your exponential, your sines, cosines, etc. So just to make sure that we have some examples, all your basic polynomials come under that. You have e to the z sum over z to the k over k factorial, sines and cosines, etc. Okay. Etc. Good. So the next thing we're going to do is where we take this beyond what we have generally in calculus. We're going to get a series expansion with all positive and negative powers of z minus z sub 0. And it follows pretty much the same construct we did here with a twist. So I'll just set that up. This next topic and object that we're about to investigate is called the Laurent series. And then we'll see immediately the Taylor series is a subset of the Laurent series in general. And what we're going to do is consider f analytic in and on C. I'm going to define this contour carefully. So we'll put z sub 0 at the center of two concentric circles again, okay. But with a bit of a twist. Namely, the regions, the contour is this combined contour here. Let me do it. So if we were to come around here the way we do, counterclockwise, and then go in here clockwise, around, and back out. Okay. So the region that our function is analytic on is the annulus. So in and on C, also analytic on the annulus. And so this entire thing is C, that was a comma, and C is equal to C1 plus C2, and we're letting C sub 1 be the outside, I believe. and C sub 2 be the inside. Yeah. C sub 2 be the inside. Okay. So yeah, we're analytic. The annulus here. What type of point this is, we're not even specifying yet. Okay, it's just a point about which we're going to do our expansion again. Okay. And then we'll consider just some point Z element the annulus. So Z element of the annulus here. Okay. Somewhere in between there. Good. So first of all, we have, let's multiply the whole thing by 2 pi I f of z is equal to f of zeta d zeta zeta minus z along the contour C, but now we can break it up into C1 plus C2. And so, okay, I'll write this out for actually, it's going to get a minus sign. Zeta minus C. So here I'm saying C1, here I'm saying C2. And C2 would be the proper orientation, but because for the entire thing we're going around counterclockwise, or clockwise, we've got the minus sign right there. Okay, so far so good. Now we're going to do the same thing we did up there, except I have to put a note about the distances here. So on C1, so on the outside, we have zeta minus z magnitude is greater than zeta minus z naught magnitude is greater than zeta minus z. Inside one, it's the other way around, zeta minus z naught is less. It's less than zeta minus z. Okay, the zetas are all taken from the contour. Okay. Z is some point in the annulus, so again, if you're on the outside contour, the distance from the outside contour to z sub 0, which is total radius, is clearly greater than the distance to z, regardless of where z is on the annulus. And vice versa for the c sub 2. Zeta minus z sub 0, that's this inner radius, is less than zeta minus z, which is you're somewhere outside the inner radius. So we're going to use these for our construction. And I just multiply by 2 pi I so I don't have to write it as often. Let's go ahead and erase this. So, got 2 pi I f of z is equal to, for C1 I've got f of zeta d zeta. And for C1 it's the same construction I had a moment ago. Make sure I get this right. So for C1 I've got the zeta minus z sub 0 multiplied by 1 minus z minus z sub 0, zeta minus z sub 0. I'll put these in parentheses again. Okay, just to make sure we see that. For c sub 2, zeta d zeta, c sub 2. Right. I have to have the other one in the denominator, this one, because it's larger now. Yeah, note the difference there. So I write z minus z sub 0, 1 minus zeta minus z sub 0, divided by z minus z sub 0. And that's c sub 2. Yeah, so make sure you see this. Here we cancel that, so it's just zeta minus z sub 0 minus z plus z sub 0. That one works. This one here, and cancel there, so z minus z sub 0 minus zeta plus z sub 0. So I've got z sub 0 minus zeta as opposed to zeta minus z, but I'm getting rid of that minus sign, and now both of these are just in the proper orientation around these contours. Okay, so here it was a minus, a negative orientation. Now it's back to the positive, got rid of that sign difference. And so what I get on this integral is what we had before. It's just going to be our Taylor series terms. Let's go ahead and do it. Zeta. Integrate. And then the summation here of z minus z sub 0, zeta minus z sub 0 to the nth power. So this is what we just did. Trying to give the same result. Here, it'll be a little bit different. F of zeta d zeta. Now we have z minus z sub 0. Let's put that summation. Okay. See, this is inverted here, but again, this is a 1 minus some complex number, and this complex number has a magnitude less than 1, so that's why we can do this series. Zeta minus z sub 0 to the nth power. Good. So continuing, I'll erase all this. Okay, here nothing has changed. And we'll just put big parentheses around here. We've got zeta minus z0 to the n plus 1. And what's left is z minus z0 to the n. And actually I'll put the summation out here. That looks better, right? Integral. Yeah, so that again is just the Taylor series. Those are the coefficients, c sub n, and they mean what they did before, the nth derivatives. Now let's look what we have here. So we can do the summation outside. We have integral f of zeta d zeta. And we have, actually we can keep this in the numerator for the moment. Keep this in the numerator for this time right here. So we have zeta minus z sub 0 to the n. And now we have these inverse powers, z minus z sub 0, 1 over z minus z sub 0 to the n plus 1. So that's where the inverse powers are going to come in. Also, n equals 0 to infinity right now. Since this is just the Taylor series part, we're just going to check it off. That's what we did before. This one we have to work with a bit. I'm going to change the number of the index. I'm going to go from n equals 1 to infinity instead of 0. Then I have to change these indices here. C2, got my f of zeta, d zeta. So this has to now be n minus 1. N minus 1. And then I have to have z minus z0 to the nth power. And the last step I'm going to do is just change these n's to negative n to negative n, and make the corresponding changes on these right here. See what we have here. N minus 1. N, very good. Good. All right, we have obtained f of z equals the sum over c sub n z minus z0 to the nth power. N goes from minus infinity to plus infinity with c sub, c sub n is equal to 1 over 2 pi I f. We went ahead and divided by 2 pi I now. F of zeta d zeta. And actually, I'm going to put a tilde here. I'll have to discuss that in a moment. Zeta minus z sub 0 to the n plus 1. So we have to convince ourselves that this holds true for the negative powers as well, because it's really nice. It's just that one uniform expression that we had before. And you'll see it here. So we're turning this into a sum from minus 1 to minus infinity. And so when you take the minus 1 down here, right, you end up with these in the denominator, and then, yeah, that's fine. These negative powers are taken care of right here. You just go from minus infinity to 0. So that does the trick. Now, as far as this C tilde, that's an important note, and you could leave some room in your notes to demonstrate this. C sub tilde is any circle, and that can be generalized to any contour that is between, so any concentric circle for starters between C1 and C sub 2. So that takes a little bit of working with. Remember, we had Z sub 0 in the middle, and these two concentric circles. But what you'll see is, if you take, and you've got your Z somewhere here, if you take both of your integrals about, say, this red one here, you can always realize that construction. So the above construction that we just did will always be realized with this. And it'll be because you'll be able to take the differences between the contour and the inner point versus the contour and that Z point as being either, you know, greater or less than. So above construction can be realized using C tilde. And C tilde is just this red one right there. So that makes the whole thing very compact, right? You've just an extension of your Taylor series down into the negative powers. The same formula covers all of them. What we're going to see is we're generally not using this formula to calculate the coefficients. We're constructing the power series and just taking the coefficients that we find by construction. And I'll demonstrate that in a moment. But yeah, this is our Laurent series. And because it has these negative powers, we're going to have a classification of singularities, because you see once you're 1 over x or 1 over z squared, etc., you have singularities right built into your function. Okay, I think that suffices for now. And I'll give a couple of examples just to see how we go about this. So make sure you leave plenty of room in your notes, because you want to really recognize what we did here. Okay. And then, you know, any missing steps there, you go over them, you'll see exactly how that worked. Good. Okay, let's check the time before anything else. Okay, excellent. Let's do this. I have a couple of examples. So suppose we had f of z equals 1 over z, 1 over z minus 1. And we want its Laurent series. We could call that negative 1 over z, 1 over 1 minus z. Right? This thing plays such a big role. And we'll see immediately, negative 1 over z. Now we get the power series of this one, z to the n. N equals 0 to infinity. Now we can write this out. 1 plus z plus z squared. So what do we have? What have we arrived at? Minus 1 over z. And then we'll just have the rest of these plus 1 plus z. So on. So this function has this Laurent series about 0, and clearly because of where this thing came from, you know, we know the convergence of 1 over z, 1 minus z. So where this thing came from tells us that this is for z less than 1. So that's the Laurent series for z less than 1. Now, do we want to do, yes, now what about for z greater than 1? Use this part of the board. Same f of z magnitude greater than 1, so outside the unit circle. We want to do a trick, so we'll have f of z equals 1 over z. Z minus 1. So we're going to do this. 1 over z squared. So we'll pull out another factor of z here. We'll have 1 minus 1 over z. I just pulled out that extra factor z here. 1 over z. And now I have 1 over z squared. Sum over n equals 0 to infinity. 1 over z to the nth power. And you can see that's a different series entirely. Looks like a different series at least. Let's go down here, we've got a little more room. And wrap that up. So what do we have? We have 1 over z squared times 1 plus 1 over z, and so forth. Okay. And that gives us 1 over z squared plus 1 over z cubed, and so forth. Okay, so yeah, make sure we put these together here. You can see the very different appearance of them, but this again, this is for z outside the unit circle, and this is for z inside the unit circle. So yeah, they're both examples of the Laurent series. This one has that one pole. Okay. This one has all the infinite powers of that pole. So that's what we're going to end with today. Actually, I think I'll start with these self-same examples next time. It's a very nice basic function. You can see the two different regions in which they're defined, two different Laurent series. And these have okay, good. So we'll leave it at that. I think that's a good place to stop. Okay, good. See everybody next time.